Hi, in the previous video we've learned how to multiply matrices. Now we're going to focus on vectors, but remember, of course, the same rules that apply to multiplication of matrices also apply to multiplication of vectors. But because they usually come with some special meaning in both mathematics and economic problems, now let's concentrate a little bit on multiplication of vectors. Okay, let's just say that we've got two column vectors. Vector u equal to given by u1, u2 until some un, right? Now, what is the dimension of this vector? It's n by 1. N rows, 1 column. Now, let V be another column vector, v1, v2, vn. This vector is also of the size of the dimension n by 1. Now let's see if we can multiply those vectors. Okay, so u times v equals to, what do we see here? Well, the first one has dimension n by 1. Well, the second one has also dimension n by 1. Can we multiply them? Well, we clearly see that those two are different numbers, so definitely we cannot multiply those two vectors. Okay, so if we cannot multiply those two vectors, maybe we can multiply two row vectors. Row vectors we will denote as u prime and v prime. What this prime means I will explain later. And look, u prime vector will look like this: u1, u2 until u. Again, v prime vector will look as v1, v2 until vn. Now, can we multiply those two vectors? Okay, so it's u prime. Oh, okay, let's put their dimensions first. 1 by n, 1 by n. So u prime times v prime, we've got 1 by n and 1 by n. Can we multiply them? Well, we can't. Again, those two dimensions are different, so we cannot multiply them. Well, so we get another empty set. So, does it mean we cannot multiply the vector? Well, definitely not. We definitely haven't explored all of our possibilities, right? What if, for example, I would like to multiply vector u by vector v prime? Okay, so what do I have? Oh, maybe I'm going to do it over here. Vector u times vector v prime. Look, this vector is n by 1. Well, this vector is 1 by n. So, we clearly can multiply them because those dimensions are identical, and as a result, we should get a vector, and we should get a matrix with the dimension n by n. Okay, so how would we do it? So let me put just vector u, 1, u2, un. Here we will have vector v1, v2, until vn. Okay, so what will we get? But remember, when I multiply two vectors, when I multiply generally two matrices, I multiply each full row of the first matrix by each full column of the second matrix. But look, here rows are just individual elements, and here columns are just individual elements. So look, what we will get is a matrix of all possible products of all these vector elements. So look, first I will multiply first row by first column, u1 times v1. And over here, first row by second column, u1 times v2. And so I will be multiplying by u1 by v1, v2, v3 until v. I would get u1, v, n. And now I need to just do the same thing, but for the second row. So I will have here u2, v1, u2, v2, u2, v, n. And of course, we would be going like this until we arrive at the last element in vector u. So un, we would have un, v1, un, v2, until un, v, n. And definitely we see this matrix will be of dimension n by n. Okay, so we see that if we're gonna take a column vector u and we're gonna multiply it by a row vector v, we're gonna get a matrix of all possible products. Okay, but of course, those two dimensions don't need to be the same. And look, let's see an example of how it's done on numbers, and I think it should explain the entire procedure very well. Okay, so now we've got vector u and vector v prime, and we've got the u is 3, 2, and v prime is 1, 4, 5. Okay, so this vector is 2 by 1, and this vector is 1 by 3, right? So, as an outcome of multiplication, we should get a matrix 2 by 3. Okay, so first, 3 times 1, 3. 2 times 1, 2. 3 times 4, 12. 2 times 4, 8. 3 times 5, 15. 2 times 5, 10. So this is how we multiply when the first vector is a column vector and the second vector is a row vector. Okay, but what if we would reverse the places? What if first we would have a row vector and then the second vector would be a column vector? Okay, so now we will have vector u prime and we multiply it by vector v, right? Now, dimension of the first one is 1 by n, and dimension of the second one is n by 1. So, if I'm gonna, can I multiply that? Clearly, because they have those dimensions identical, and as an outcome I should get a matrix 1 by 1. Okay, so what does it mean? Let's do this one slowly as well. So we've got u1, u2, and some un, and then we've got a vector v. v1, v2, until vn. Again, when I multiply matrix by matrix, I go entire row by entire column. Here is just one row, one column. So what will I get is u1 times v1 plus u2 times v2 plus until un vn. So what will I get as an answer? I will get just one single number. So in this particular case, we see that actually the outcome of multiplication is a scalar, a number, right? So let's just do one example on this, and we'll see what we are getting. Okay, so we've got vector u prime times vector v. Vector u is 3, 4, while vector v is 9. Okay, we clearly see that this one is 1 by 2, this is 2 by 1. Can I multiply them? Of course. So let me proceed. Okay. I will have 3 times 9, 27, plus 4 times 8, 8. So, if I add those two, I'm getting 55. But, as we said, this is just a number. So, I can get just one single number. And look, what we are getting in this particular case is something that we call scalar product. Because when we multiply everything out, we just get a scalar. Okay, so now we know how to multiply vectors. But maybe we should take an advantage of the fact that we can actually draw vectors to see how everything, how all the operations of the vectors work. Okay, but because we need to draw just in two-dimensional space, we will have only vectors with size 1 by 2 or 2 by 1, right? Now, the thing is that everything that we're going to say here can be easily generalized to three-dimensional space. But in three-dimensional space, of course, it's becoming really hard to draw. Well, when it comes to four-dimensional space, well, it's impossible. Well, we live in three-dimensional world, so we cannot go beyond the boundaries of three-dimensional world. Although, still, on paper or on a computer, we can calculate it quite easily. Okay, so let's move to geometric interpretation of vectors. Okay, and let me first define you something called radius vector. So, radius vector is simply vector starting at the origin in Cartesian coordinate space. Okay, those are the vectors we will be dealing with. Okay, so let's start by having two vectors. Vector u 2 by 2. 2, and vector v 9, 7. Okay, no, it will be too complicated to draw, and it's 1, 9. Okay, so look, first let's just draw those vectors in the coordinate space. Okay, so now, we will treat that x is the first coordinate or y is the second coordinate, which is a very rational choice. Of course, here we have the origin, the point where both then we've got 1, 2, okay, we will need, probably we'll need 3 later. We've got 1 and 2 and 3. Okay, so how do I graph a radius vector? Actually, this is really easy because as the definition suggests, we should just start from the origin. Where should we finish? At the coordinates given over here. So, vector u in our scenario will be vector coming up from the origin. And going into point 2, 2. Look, as you might notice, I did not just connected those 2 points with a line, but I also put a arrowhead over here, right? Why do we do so? Well, by definition, vectors are ordered pairs of points. With radius vector, we are assuming that they are starting at the origin. So of course, the direction indicated by this vector must be pointing to that point 2, 2. Okay, so then we need to have the second vector, vector v. Let me denote it by red color. And this one has x coordinate at 1 and y coordinate at 3. So again, okay. Now that we've got these vectors, we can perform different operations on them. So let's start with addition. So what I want to do now is to add vector u to vector v, and I'm going to see what happens. Look, we already know all the rules on vectors, on operations on matrices, especially in case of adding. So this task should be really, really easy, right? They both have the same dimensions, so we can definitely add them. Conformability conditions are met. So why not? We will get that this is 3 and 5. Now, how would we see this in coordinate space? Well, because it's really hard to draw, I'm going to start by putting the appropriate point over here. Okay, this is where we need to end up. But how should what should be the geometrical procedure to graph it? Well, in this procedure, we use something called parallelogram. Parallelogram I think it's with 2L. Yeah, parallel here with 2L. Parallelogram. Parallelogram is something that you know very well from high school. Something that looks like this. But on a condition that those two sides are parallel, just as well as those two sides are parallel. And we will use parallelogram to create this new vector 3, 5. Okay, how do I do it? Look, imagine that this arrow is going here further and further and further, right? And now look, what if I would take this arrow and I start moving it upwards, 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 upwards? So I will take the same vector as you see over here, and I will put it over here, start starting at this point, but of course with the same angle as over here. Then I could do the same thing for the other vector. Now I would take this vector, move it over here, and try to slide it until this point. No, maybe this time without arrowheads. Okay, and now look, finally, if I'm going to say at the point of intersect of these two lines, we will have the new arrowhead of a vector u plus v. Okay, so the new vector will be starting at this point and ending up at point. It started at the origin and ending up 3, 5 point. Okay, I hope you've seen it already somewhere in high school, and I don't think this is a very problematic thing. So let's move on to the next operation. Okay, now let's just say that what we want to do is we want to try multiplication by scalar. And this time we're just going to stick with vector u. So, scalar, of course, I hope you remember quite well, takes its name from the fact that it scales matrices up or down. But as you will see over here, it can do way more. Okay, so now we'll just concentrate on vector u. We've got 1, 2, 1, 2. Okay. We will need a little bit more space, so let me just, okay, I think this is going to be enough. So, again, I'm going to start by simply drawing vector u. And what do we see? So we see the same vector u we had before, right? Now, okay, let's forget about vector v. We are not using it. And let's just say that what I want to get is vector 2u. Okay, again, I can simply use what we've learned previously. This should be our vector 2u. Does it make sense? Look what has happened. Now, the vector that we are interested in still starts at the origin, goes through the old vector, but it ends up at this point. Of course, if my drawing would be better, you would actually see that those two distances are identical. So what has happened? When I multiply it by 2, I actually created a vector twice as long. Okay, so what would we get if we wanted to have 1 over 2u as vector? Well, we would multiply our vector by 1 over 2, and we would get, you see, 1 and 1. So, if I want to draw it, we see that now we actually, all we've got 1/4 of vector 2u. Okay, and look, this is the scaling effect. By introducing a positive number on a vector, we are scaling it up or scaling it down. But is it really all that we can do? We can do more. What if now I would be interested in drawing vector negative u? That would be simply -1 times 2 twice, -2, -2. So, what would we see right now? That the vector that we used to have has actually changed direction to the opposite. So, you see, now we are going simply in the opposite direction. So the arrowhead is pointing down. So pointing to the southwest, right? Okay, and this is also a very important property because it will allow us to actually create a procedure for subtraction of vectors. Okay, now let me erase this because now we will need way more space. Erase this. Okay. Okay, and we will be using the same two vectors. So vector u, 2, 2, and vector v, I think it was 1, 1, 3. Yes? Well, yeah. 1, 3. Okay, and look, now the task that we've got is subtraction. So, we've got vector u, and I need to subtract from it vector v. Well, doing this graphically might be a little bit problematic unless we realize one very simple thing. Look, subtracting vector negative v is the same. Subtracting vector v is the same as adding vector negative v, right? So if I actually want to draw this vector, all I have to do is to first build vector negative v and just add them using parallelogram exactly the same way as I did before. Okay, again, maybe let's start by calculating the exact values. So we will have 2 minus 1 is 1, and 2 minus 3 is negative 1, right? Okay, so this is the vector u minus 1. Okay, so again, let's use colors for everything. So first we draw vector u. And then making vector v. Okay, so we see that in our procedure, first thing we should do is to create vector negative v out of vector v. So look, vector negative v would be exactly the same. But the values, the absolute values inside the vectors would be exactly the same, but everything now needs to have opposite sign. So here I will have negative 1, and here negative 1, negative 2, negative 3. Okay, so let me connect those points. Okay, and I've got vector negative v. Okay, and so how can we end up like this? Well, now situation is slightly more problematic, right? Because I need to create parallelogram, but arrows are pointing a little bit differently. But look, this is not a problem because we could do this exactly the same way. So I'm going to be using, let's just say, this color for the lines. First, I'm going to take this line, put a parallel line over here. We need to end up at 1 and negative 1. And look, I'm taking this line and I'm moving it parallelly until it touches the arrowhead of this vector. We are imagining that this line is a perfectly straight line. And then I do the very same thing over here. I'm taking this line and I'm moving it parallelly until I reach this arrowhead. Okay. Now, all we need to do is to go from the origin and make our final vector. Okay, so I think this is enough about vectors for now. In the next video, we will start tackling different operation laws on matrices. Thank you for your attention.